Hi, let's start with Chapter 2, Frequency Distributions. After this chapter, you will be able to understand how frequency distributions are used. You will be able to organize data into a frequency distribution table and also into a grouped frequency distribution table, and you will know how to interpret frequency distributions. Lastly, you will be able to organize data into frequency distribution graphs and also know how to interpret and understand graphs. For this chapter, you will need to know how to do proportions. So you will know how to do fractions and decimals and percentages and go back and forward from one to the other. So make sure, if you're not that comfortable with it, that you look at the math review in Appendix A of the book to kind of do a refresher on that. And then you also need to know the scales of measurement that we covered in Chapter 1, so the idea of a nominal, ordinal, interval, and ratio variable, and also the distinction we made in Chapter 1 between continuous and discrete variables. And then another thing you're going to see that's going to come up in this chapter is the idea of real limits that were also covered in Chapter 1. A frequency distribution is an organized table or tabulation that shows the number of respondents or individuals in each category on a scale of measurement. So this could be, for example, in a table. This would look like that. So here you have the responses of young boys when they had a toy taken away from them. So you can see that we had 25 boys that cried, 15 that were just mad, 5 of them just withdrew, and then 5 just said, oh well, play with another toy. So you can see that a table, a frequency distribution table, has to have certain things. So the first thing, it has to have a title, so we know what it is that we're looking at. So in this case, responses of young boys to removal of toy. Then it needs to have the categories. So here we can see that the responses of the children were different. So some cried, some were mad, expressed anger, some just withdrew, and some just played with another toy. And then we have the frequency for each of the categories. So we can see that we had 25 boys that cried, 15 boys that expressed anger, 5 that withdrew, and 5 that played with another toy. So the frequency is the number corresponding to each of the categories. And then we have the sum of the frequency, which is the same as n, or our number of people in the sample. So in this case, adding 25 plus 15 plus 5 and 5, we can see that we have 50 people in this sample. You can also show tabulations in graph. So here is exactly the same table, but represented in a graph. So this is a frequency distribution of the responses of young boys to removal of toy. And again, here you can see we have the frequencies on the y-axis, and then on the x-axis we have the categories. So here again are our 25 that cried, here are our 15 that expressed anger, 5 of them withdrew, and 5 played with another toy. There are certain rules on how to show a distribution or frequency distribution for one variable, depending on, is it a nominal variable, an ordinal variable, or an interval ratio variable. So again, that's why the distinction is very important. So let's take a nominal variable first. So we learned in Chapter 1 that marital status is with the categories being married, single, and previously married, for example, would be a nominal variable, because the categories are just arbitrarily named, right? Married is not better or worse than single, or not higher or lower than previously married. There's no order to these, so that's a nominal variable. And so you can see that we have, again, by our rules, marital status with the categories first in the first column, and then in the second column the frequency. So in this case we had 30 people that were married, 20 that were single, and 10 that were previously married. So we had a total number of people, or the sum of all our frequency, 60, right? The 30 plus 20 plus 10. So we have 60 people in our sample. And the important thing is that nominal distributions can be listed in any order because those are just arbitrary names. So for example, we could have also displayed this table in this form: marital status, single first, previously married, and married first. And since there are 3 categories, we could have also displayed it like this. So it doesn't matter which of the categories we would list first, because only for nominal variables, only the frequency is appropriate. The frequency table for ordinal and interval and ratio variables has exactly the same structure as it does for nominal variables. But the categories in an ordinal and interval variables must be in sequence order, so we can use it for statistical purposes. So if you look here, we have a frequency distribution of attitudes towards a proposed tuition hike on a college campus. So here we have attitude towards a tuition hike, and then the different attitudes: strongly favorable, somewhat favorable, slightly unfavorable, somewhat unfavorable, and strongly unfavorable. So you can see there is some order to this, right? Strongly favorable, somewhat favorable. So we've gone from strongly favorable all the way to strongly unfavorable. So it doesn't make any sense if we would shuffle the categories like we were able to do in a nominal variable. So we couldn't do slightly favorable, somewhat unfavorable, strongly favorable, slightly unfavorable. It doesn't make any sense. They have to stay in order if we have an ordinal variable. So in summary, when we look at the frequency distribution tables, the structure is that we have the categories in a column, and they are often ordered from lowest to highest, but it could be reversed, so it could be highest to lowest, and you will see that a lot in the textbook. Then you have the frequency count next to the category, so they on the right next to the category, the next column. The sum of the frequency is the same as the number of our people in a sample, the number of respondents. To compute the sum of x from a table, you either have to convert the table back to original scores, or you have to compute the sum of f times x. Constructing either frequency distributions or grouped frequency distributions for discrete variables is uncomplicated, because individuals with the same recorded scores had precisely the same measurement. So the score is an exact score. So if we look again for the example at marital status, you either are married or you're single. You cannot fall within these two categories. So you either have check the category married, or you check the category single or previously married. You fall exactly into one of those three categories. We can easily group frequencies into a grouped frequency distribution table. If the number of categories, for example, is very large, we usually combine them. So we group them together to make the table easier to understand. And I'm going to show you an example on the next slide. However, you'll see that you lose a lot of information when categories are grouped together, because these individual scores that you now combined cannot be retrieved anymore. And of course, the wider the grouping interval, the more information is lost at the end. So let's just look at this table of a frequency distribution of final examination grades for 71 students as an example. So you can see there's a lot going on in this table. So we actually have scores from 50 all the way up to 99, but you really cannot see very easily what exactly it is that's going on. So it might be better to make little, which is called class intervals, out of the data. So maybe we want to group them together. But remember how I just said that information is lost when categories are grouped and individual scores can really not be retrieved? And also that the wider the grouping interval, the more information is lost. So if I would, for example, make this class interval of scores of 95 to 99, then you can see that I would have now 3 people in this one category, scoring between 95 to 99. But once I have that, I would not be able to see anymore who exactly scored 198 and 196 and 195, because that would be gone. I would have 3 people in the category of 95 to 99. So here's what this table might look like after we're done with creating class intervals. So you can see now it says 95 to 99, 90 to 94, and so on. And now you can see we have 3 people in the class interval 95 to 99 that I just mentioned. But again, back to my point, we lost the individual data. So if we only have this class interval of 95 to 99, if somebody would ask you, well, how many people scored 97? We really don't know that anymore because we lost the individual data. What's important is that these class intervals are not just arbitrarily made. So we can't just decide, oh, we want to take 95 to 95. But there are certain mandatory requirements and suggested guidelines. So let me show you how those intervals are made. For class intervals, we have mandatory requirements and just some guidelines. The requirement is that all class intervals must have the same width. The guideline is that you should end up with about 10 intervals. So if you have 9 or if you have 11 or 12, that's fine. They should be around 10. Again, if you have 20 intervals, then you still have your data way too big, right? The table is still kind of messy. But if you scrunch them together, so if you have only 5 intervals left, then you lost a lot of the individual information because you scrunched them together so much. And then also you want to choose simple numbers for interval width. Let me show you what this looks like. So step 1 is in order to make a class interval, we get the range. And the range is just simply the highest score in your data set minus the lowest score in your data set. So if we take our grades from the previous example, then our range is 99, which was the highest score, minus 50, that was the lowest score. So the range is 49. The next step is that we want to get about 10 intervals. So we take our range, the 49, and divide it by 10. In this case, we get a 4.9, and that's where the simple number comes in. So 4.9 is kind of a crooked number, so we round it up to 5. So each interval should hold 5 numbers. What's important is that our lowest and our highest number in the data set have to have an interval. So in this case, if we say that each interval should have 5 numbers, we end up with, starting with the highest number, the first interval being 95, 6, 7, 8, and 9. So 95 to 99 because that holds 5 numbers. The next one is 90 to 94 because we have 90, 91, 92, 93, and 94 that fall into that interval. The next one is 85, 86, 87, 88, and 89, again holding the 5 numbers, and so on, until we have an interval for all of the data. Constructing grouped frequency distributions for continuous variables also requires an understanding that a score actually represents an interval. Consequently, grouping several scores actually requires grouping several intervals. And this is where the concepts of apparent and real limits comes in. Apparent limits of the grouped class interval are always 1 unit smaller than the real limits of the grouped class interval. So why is this? Because the real limits extend half a unit above and half a unit below each score. So the upper apparent score actually includes half a unit above it, and likewise the lower apparent score actually extends half a unit below it, and that half a unit plus half a unit is this 1 extra unit that is included between the real limits that then is included between the apparent limits. Let me show you again what this looks like. So again, looking at our example of the grades before, so we said that the class interval in this case is 95 to 99. And this is what's called the class interval, and that is the apparent limit. The real limit, however, is everybody that scored between 94.5 to 99.5, because if it's considered a continuous variable, because the real limits extend half a unit above and half a unit below the score. So 95 and half a unit below that is 94.5, and 99, half a unit above that, is 99.5. Frequency distribution graphs are just pictures of the data organized in tables. So all of the graphs have 2 axes. The x-axis, which is typically displaying the categories of measurement, and what's important is that it increases from left to right. So if we look at the x-axis, so this is usually the categories are displayed down here, it increases from here to there. So here would be the 0, and then it goes 1, 2, 3, 4, whatever our numbers, and it increases to the right. The y-axis has frequencies usually, but a lot of times we can have percentages, or we're going to talk about all that later. So right now, just frequency is important, and it increases from the bottom to the top. So it increases from down here again, we would have 0, and this is where y and x meet, right? It's 0. I'm sure you remember that from your math classes. And then it increases from the bottom to the top, and that's the y-axis. The general principles are that both axes should have a value of 0 where they meet, and then usually when we draw them, and we're just going to do a lot of rough drafts in this class, then the height should be about 2/3 to 3/4 of the length. There are certain questions we have to ask ourselves before we start graphing a table. So before we want to represent our table in graph form, because the answers to these questions determine which one is the appropriate graph, because the graph really depends on the level of measurement. So are we talking about a nominal, ordinal, interval, or ratio variable? Is it a discrete or continuous variable? And are we describing samples or population? So the answers to these questions determine which is the appropriate graph. The appropriate graph for nominal or for ordinal data is what's called a bar graph. So you can see here we have a bar graph showing the distribution of personality types in a sample of college students. Because in this case personality type is a discrete variable, so you can either be personality A or B or C, and there's no continuation between the three categories. This is a nominal variable. The graph in this case is then drawn with spaces between the bars, showing the bars not touching, right? That shows that it's a discrete category without, in this case, a particular order, because you could have personality type B before A and C and so on. And you can see we have the characteristic here, personality type, and the frequency on the y-axis. Another example could be this graph for bar graph for seat belt use. In this case, again, frequency on the y-axis, and then the idea of never, seldom, sometimes, most times, or all the times of seatbelt used are on the x-axis. And this is, again, an ordinal variable, but there is no continuation between never and seldom. Either you said you never wear your seatbelt, or you seldom wear your seatbelt, or sometimes, most of the times, all of the time. You can see there is some order to these categories. So a bar graph is appropriate for nominal and for ordinal variables. Here's another example of a bar graph, and again this is for seatbelt use, but in this case you can see it is the percentage instead of the frequency that is displayed on the y-axis. When we have interval or ratio data, we need to do what's called a frequency distribution histogram. It represents all scores on the x-axis from minimum through maximum observed data values. We need to include all the scores, even the ones with a frequency of 0, and it's simply done by drawing bars above each of the score. The height of the bar corresponds to the frequency, and the width of the bar corresponds to the score's real limit, or 1/2 score unit above or below discrete scores. So it sounds a little bit more complicated than it actually is. So if we just look at a frequency distribution histogram, for example, of quiz scores, and you can see again frequency is on the y-axis, the quiz scores are on the x-axis. This would be our table corresponding to this, and we have one person that scored a 1, 2 people that scored a 2, 4 people that scored a 3. If you just look at the graph itself, right? Also, again, you can look at the table, but you can see it kind of looks like a bar graph, but a histogram. In a histogram, the bars are actually touching, so it shows a continuity between the different categories. So they're not distinct categories, but they kind of there's a continuation between them. So that shows the histogram that the bars are touching. Here's another example of a histogram for stress and memory recall study. So again, frequency on the y-axis and the number of words that were actually recalled under stress, and in this case it shows the real limits from 24.5 to 29.5, and which were our apparent limits would be 25 to 29, 30 to 34, 35 to 39, right? A histogram showing the continuity along a scale. When we look at a group frequency distribution histogram, we can see it has exactly the same requirements as the frequency distribution histogram has, except for that you need to draw the bars above each grouped class interval. So the bar width is the class interval's real limit. So in this case 29 and a half, you see how it starts right here, right? It doesn't start at the 30. 29 and a half to 31.5, and then 31.5 to 33.5. And the consequences of this are that the apparent limits are extended out again 1/2 score unit at each end of the interval. So in this case it's children's heights in inches, and that's again because height is a continuous variable, right? A histogram can be made into a block histogram. So basically you're just creating a bar of the correct height by drawing a stack of blocks, and each block represents one case. So in this case, one person, one block, right, scored a 1, 3 blocks for 3 people that scored a 2, 3 scored a 3, and so on. Another graph we use for interval or ratio variables is what's called a frequency distribution polygon. And the polygon is best suited to emphasize continuity rather than differences. So you always represent the frequency distribution of a single variable. So this just shows, in this case, scores. And then again, here we have the frequency. So you list all numeric scores on the x-axis, including those that have a frequency of 0. We don't have anybody with 0 here, but we had one person that scored a 6. So you put a little dot on the 6. 2 people scored a 5. So here's the 5. 2 people, right here, the 2 people scored a 5. So you put a little dot right there. So you basically draw a dot above the center of each of the intervals, and then the height of the dot corresponds to the frequency. And then you just connect the dots with a continuous line. What's important is that you close the polygon with lines down to the y equals 0. We didn't have, no person that scored a 0, but we just kind of close it out. And that's common, that we just close it out, the polygon. A polygon can also be used for group data if you want to display group data frequencies. And here's an example. Let's say we have an interval from 12 to 13, so we grouped it, right? And then here are the scores, and we had 4 people that scored between 12 and 13. So you can see this is this point right here. So it's the same as it was for the regular polygon. You just use the midpoint. So if you have 12 to 13, 12.5 is the midterm. Let's look at the 4 to 5. So you would have right between 4 and 5 would be those 2 people right here. It's really important to be able to read graphs because they are very easy to mislead people into believing something that's not actually there. So in this case, you can see there are 2 graphs showing the same number of homicides in a city over a 4-year period. And in the first one, you can see number of homicides, and then it looks like it increased dramatically, right? And so in this case, if I, for example, I'm a police captain and I want to have more police officers, more money for police officers, I would say, look at this data. It increased dramatically between 2005 and 2008. But if I'm, for example, a police captain that wants to show how great I have been doing since I've been here since 2005 to 2008, this is exactly the same data set. But you can look at, it seemed like almost, it just increased slightly. And exactly the same data, but it all depends on how we are squishing together our y-axis or how we are dragging it apart, right? In this case, the columns look so much bigger, and here they look close together. So it's easily used for misuse. Researchers can describe a distribution's shape in words rather than just drawing it. A symmetrical distribution just means that each side is a mirror image of the other. So basically, if you would fold them in half, they would be exactly the same on each side. In a skewed distribution, the scores pile up on one side and taper off in a tail on the other side. The tail, if the tail is on the right, so that means high scores on the right, then it's positive skewed. And if the tail is on the left, referring to the low scores, then you have a negative skewed distribution. So what do you think is the shape of this distribution then? Is this a symmetrical one, negatively skewed, positively skewed, or discrete? Well, discrete is not really explaining the shape of a distribution. Symmetrical means if we fold it in half, does it have exactly the same shape on each side? It clearly doesn't. So this only leaves a negatively skewed or a positively skewed. And remember I said it's all about where the tails point to. In this case, the tails point into the tail right here points into the positive direction, right? Because this again is increasing into this direction. So this is the positive side. So this is a positively skewed distribution. So the correct answer is C. Congratulations! You made it through another chapter. See you in the next chapter.